Welcome to Module 2 of this course on circuit analysis. Resonance, coupled circuits, transient analysis, and two-port networks. 1. Resonance in electrical circuits. Let's start with resonance, which is a special condition that occurs in AC circuits containing inductors and capacitors. Think of it like pushing someone on a swing. If you push at the right frequency, the swing goes higher and higher with minimal effort. That's resonance in mechanical terms. In electrical terms, it's when the effect of inductance and capacitance cancel each other out at a certain frequency, resulting in either a very high or very low impedance, depending on the type of resonance. There are two main types. Series resonance. Here, an inductor and capacitor are connected in series with a source. At the resonant frequency, the inductive and capacitive reactances cancel, and the circuit behaves as if it's purely resistive. Current reaches its maximum value for a given applied voltage. Parallel resonance. In this case, the inductor and capacitor are connected in parallel. At resonance, the current through the branch is minimized, and the total impedance of the circuit is at its maximum. Key parameters in resonance include bandwidth, the range of frequencies over which the circuit responds significantly. Q factor, a measure of how sharp or selective the resonance is. Higher Q means a narrower and sharper resonance peak. Selectivity, the ability of the circuit to select or reject specific frequencies. These concepts are critical in radio receivers, filters, and communication systems where frequency discrimination is important. 2. Coupled circuits. Now let's move into coupled circuits, circuits where inductors influence each other through a magnetic field. When two inductors are placed close enough, the changing magnetic field of one induces a voltage in the other. This is the basis for transformers, wireless charging, and many communication systems. Key terms here include self-inductance, the property of a coil that opposes changes in its own current. Mutual inductance, the property where a change in current in one coil induces a voltage in another coil. Coefficient of coupling, a number between 0 and 1 that describes how effectively two coils share magnetic flux. Dot rule, a marking convention used on diagrams to indicate the relative polarity of the voltages in coupled coils. We also classify coupled circuits based on how the inductors are connected. Series connection of coupled inductors, where coils are connected end-to-end and their inductances combine according to the coupling. Parallel connection, where coils are connected in parallel, requiring careful consideration of their mutual effects. Tuned coupled circuits, such as single-tune and double-tune circuits, are used in filters and amplifiers to select desired frequencies while rejecting others. 3. Transient analysis. Transient analysis deals with how circuits behave immediately after a change in their input, such as when a switch is closed or a sudden voltage is applied. Electrical circuits have components like capacitors and inductors that store energy. When we change the input, these components don't allow the voltage or current to change instantly. Instead, the circuit undergoes a transition called a transient before settling into a steady state. We typically look at natural response, how the circuit behaves based only on its stored energy, with no external forcing. Forced response, the part of the response due to the applied external source. Complete response, the sum of the natural and forced responses. Let's break it down by type of circuit. RC circuits involve resistors and capacitors. Voltage across the capacitor changes gradually when a step or impulse signal is applied. RL circuits involve resistors and inductors. Current through the inductor changes gradually because inductors resist changes in current. RLC circuits contain resistors, inductors, and capacitors together, leading to oscillatory behavior in some cases. Common excitations for transient analysis include step signals, impulse signals, exponential inputs, and even sinusoidal sources where you want to see the complete transition into steady-state behavior. 4. Two-port networks. Now, let's finish this module by exploring two-port networks, which are a way of representing complex circuits with just two input and two output terminals. These are especially useful in communication systems, filters, and amplifiers because they allow you to describe an entire subsystem with a small set of parameters rather than dozens of equations. The most common parameter sets are Z parameters, impedance parameters, relate voltages to currents using open circuit measurements. Y parameters, admittance parameters, relate currents to voltages using short-circuit measurements. ABCD parameters, transmission parameters, describe how signals travel from input to output, often used in cascaded systems. H parameters, hybrid parameters, mix voltage and current relations, often used in transistor modeling. You can also interconnect two-port networks, for example, connecting them in series, parallel, or cascade, and calculate the resulting parameters from the individual networks. An important note is that certain networks, like symmetrical T and pi configurations, have specific properties that make their analysis even simpler. 5. Wrapping up the course. We've now covered Module 1, the foundations, Ohm's law, Kirchhoff's laws, mesh and node methods, network topology, and the main network theorems for DC and AC circuits. Module 2, more advanced topics, resonance, coupled circuits, transient behavior, and two-port network analysis. By now, you should see that circuit analysis is not just about memorizing rules, it's about building a mental toolkit that lets you take any circuit, no matter how complex, and break it down into understandable parts. Every concept builds on the last, the laws lead to methods, the methods lead to theorems, the theorems lead to powerful simplifications, and the advanced concepts allow you to understand real-world systems. The more you practice, the more these principles will feel intuitive, and soon you'll be able to look at a network and predict its behavior before even writing a single equation.